This is a basic platformer style game that I created on the Arduino Uno development board, featuring custom hardware drivers for the LCD display and joystick. I did not use any third-party libraries for this project, I just used the Arduino framework and followed the datasheets of the hardware involved. The goal of the game is to reach the flag, but if you touch a spike, you lose. Pretty simple. The joystick controls the player's movements left and right, while pressing in on it causes him to jump. A quick press causes him to hop, while a full press causes a full jump. In this video, I'll walk through a little bit how I developed this game, but you can also find the full source code linked in the description below. These are the general steps that I took in order to complete this project, and I feel they make for a good outline of this video as well. And I'll talk through a little bit about each of them. The first step was to understand the hardware, and after doing some Googling, I learned that pretty much all of the 16x2 LCD displays use this HD44780 chip, and this is the datasheet for that chip. I skimmed around until I found the parts that would be relevant in order for me to plan out the wiring. This page here on pin functions is especially helpful for that. I learned that there's a register select pin, which will help us select between the two registers that are available. One is the instruction register for writing commands, such as move the cursor or clear the screen. The other is the data register, which is the data that I want to actually show up on the screen. The read-write pin, pretty self-explanatory. It'll be putting us in either read or write mode. The enable pin is what's going to signal to the LCD module that it's time for it to read the data that we're trying to send to it over the data bit pins. There are 8 of those. However, even though there's 8 of those, which makes sense because 8 bits in a byte, on page 27 it describes there are 2 modes to actually communicate with the LCD module. The first is using all of the 8 data pins in 8-bit mode, but the second option is to send 2 4-bit chunks and use only 4 of those 8 pins. I'm going to opt for this latter option because that saves me a little bit of wiring, but it should still be pretty performant. The joystick module is comparatively much simpler. There are only 5 pins here: button, Y, X, power, and ground. The button pin will be producing either a high or low signal depending on the state of the button. The Y and X pins are going to be a little bit more interesting. These will be producing some kind of a voltage that is in between 0 and 5 volts, depending on the physical position of the joystick. As the joystick moves left or right, for example, on the X-axis, that is going to be changing the resistance in the potentiometer that's internal to the joystick module, and that change in resistance is going to change the voltage that can be measured at that pin. So therefore, we'll be looking at the signal coming off of each of these pins to determine where the joystick is held in relation to each of these axes. Once I understood the hardware, it was time to do the wiring. And instead of showing you a picture of a bunch of cables on a breadboard, it's a lot clearer to show you the schematic that I created using KiCad. The box up top is the Arduino, to the left is joystick, and down here is the LCD display. Starting with the LCD, as mentioned, I want to be operating this in 4-bit mode, so I wired data pins 4 through 7 to digital pins 10 through 13 on the Arduino. I also wired up the register select and enable pins to pins 6 and 7 on the Arduino. As for the read-write pin, because I always want to be in write mode, write is active low, and it was simpler for me to just tie that directly to ground. It'll always be a low signal then. Over here in the bottom right, this is the potentiometer hooked up to the contrast pin on the LCD. That's just a little tweak so that the contrast of how black the pixels look compared to the background, you need to adjust that with a potentiometer. Then to the left here, I have the joystick. I've hooked up the joystick pins X and Y to the analog in pins 0 and 1 on the Arduino, and they need to be analog in rather than digital pins because we're not reading just an on-off state. We're going to be reading this variable voltage between 0 and 5 volts, and so we're going to need to leverage the analog to digital converter of the Arduino, which are hooked up to these analog input pins over here. And then lastly, the switch, that's another just simple on and off type input. And so I have that wired to the digital pin number 3 on the Arduino. And I also have it hooked up to a 10K ohm pull up resistor because according to the datasheet, the joystick needs to be active low for the switch, meaning that the current that is read would be dropping to the low signal when you press it in. So when it's not being pressed, I need to pull it up to the high signal here with 5 volts. The next step was to set up my coding environment and code base for the project. Instead of using the Arduino IDE, which I feel is a little limiting, I wanted to continue to use NeoVim. And luckily there are tools such as Platform.io, which there's a VS Code extension, there's a standalone IDE for it, but they also have a CLI tool, which is what I'm leveraging here. Their tool supports 1500 plus boards, and it's pretty neat. What you do is you just define this platform.io ini file in your project, and you tell it which board you're using, in my case, the Arduino Uno. And then from there, you have access, if you download the CLI tool, you can run commands like pio run -t monitor to open a serial monitor, or -t upload to compile and upload your code to the board. So I just wrapped those commands in makefile targets that made it just a little bit simpler to type. Then it was time to write the hardware drivers, one for the joystick, one for the LCD display. And I'll talk about the joystick first because it's simpler, and some of the concepts will apply then when I talk about the LCD. So here I have the header file that I wrote for the joystick library, and I start with a struct that's just capturing the pin mappings of what number pin on the Arduino is going to be tied to which pin on the joystick. And then I have these public functions here. This is basically the API that I've created to interact with the joystick. So the first is an initialization function that I'll call at the beginning. And then I have polling for the X, Y, and switch. The X and Y is going to output a value, either -1 to move backwards on that axis, a 0 to not move at all, or a 1 to move forward. And then for the joystick, initially I just had this return a Boolean value of whether or not it was being pressed. But then as I developed the application code, I realized, especially for the jump mechanics, that it's handy to know, was the button just pressed or was it just released? That'll come in handy later. So that's why I have it returning now a switch state enum rather than just a Boolean. Taking a look now at the implementation of this joystick driver. Starting with the initialization method. I'm using the Arduino framework, as mentioned, and with that comes this convenience wrapper of having a pin mode function. And what pin mode is going to do under the hood is it's going to set a bit on an internal register that's signaling to the processor that this particular pin should be in input mode. We're expecting to read something from it rather than output mode. Same thing for all of these. I'm also initializing some state, which is relevant to the switch poll function below. Starting with the X poll then, as mentioned, this is going to be an analog signal that's some voltage between 0 and 5, and therefore we're doing an analog read to get a raw value. And the value we're getting back is being piped through the analog to digital converter, ADC. On the Arduino, the ADC is 10 bits, and that means that the number it could output in theory is something between 0 and 1023. However, what I found in practice using a serial monitor and looking at the actual range is that for this particular joystick, the lowest output that it's reading is 5 and the highest is 1015. From that, what I did was I divided it by 2 to find the midpoint, and then I picked a somewhat arbitrary distance away from that midpoint to be my thresholds for considering what would be a right movement and a left movement. I also noted here that I noted the right. When you go to the right, the voltage drops. Going to the left, it increases. And therefore, I'm saying if the raw reading is less than 300, that is what I'm considering to be right, and I'm returning a +1. If it's greater than 720, that's left, -1. And then if it's in the middle, it'll be no movement, that's a 0. Same thing applies then for the Y pole. For the the switch pole function here, I had a reminder that this is an active low. So when the signal being read is low, that means it is pressed. When it's high, it's not pressed. So I do a digital read here because this is just an on and off state. So reading, is it high or is it low? And then I'm comparing that with the previous read to determine these 4 options. Now we'll take a look at the LCD driver. Starting with the LCD struct, similar to the joystick, this is just a collection of pin mappings of which pin number on the Arduino is going to be which pin here on the LCD module. I have some things about bitmaps here, which we'll come back to in a second. And then these are the main commands. This is the main way to interact with the LCD. So there's a LCD init function, clear, create character, which we'll talk about more again in a second, and then the controls as far as setting the cursor at a specific position, and then what to print at that position, whether that be a string or a code for a character. Now looking at the right, this is the datasheet again for the LCD module, and from the factory, these are all the characters that you can print just right out of the box. The way it works, assuming that you set the cursor at the first position and you want to say print an exclamation point, what you do then is you're going to be sending a byte instruction to the data register that is 0010 0001. And if you send that, that code indicates, hey, you should print an exclamation point, and the screen will do that. Pretty neat. But what you'll notice is that what is missing from this list is there isn't a stick figure, there isn't a flag, there isn't a block, and this is what I'm going to need for the game. So to solve that, there are up to 8 slots for custom characters, and this is called the CG RAM. And over here on this page, it shows that the CG RAM for each character, it is going to be a grid of 1s and 0s, 5x8 grid. And that's what I have over here. That's what I'm defining as a bitmap. There's a 5x8 array or matrix here of 1s and 0s, and that is going to indicate which tiny pixels within that character slot are going to light up. So When you have a bitmap, you can then assign it to one of these 8 addresses here, and it will behave then the same way as if you were calling one of these predetermined characters. So we already talked about the exclamation point example, but the first slot of CG RAM of a custom character is at 00000000. So if you send that as the binary to the data register, it will print your first custom character in whatever position the cursor is currently set to on the LCD. So now I'll talk a little bit about how I implemented the LCD driver. I won't go into full detail on everything, but I will share the parts that I feel are most relevant, or I also think are the coolest parts of this. Starting with these command consts. So you'll notice here a bunch of different hex numbers. I derived these from looking at the data sheet. On this page in the data sheet, we have the table, and it shows each of these different pins, the register select pin, read write pin, and then the 8 data bit pins. And in the table, whether that pin is high or low, the total combination of all of them has a meaning. And in the case of clear display, if we have all the pins set to low except for that first data bit pin, that's how we would tell the LCD to clear the display. And so I just translated, looking at the binary for these, I just translated that using a hex to binary converter so that I could write these numbers a little bit more conveniently. Instead of literally typing out 0101, hex is more convenient for that. So that's how I set these up. And then once these are set up, I can reference them in the code here. For example, in this LCD clear function, I'm calling this other function called write command, and I'm passing it that command clear that I defined up above, which is equivalent to saying in binary 1. And so that I have a write command and I have write data, and both of these are just a little bit more convenient wrappers for the code, but what they're calling under the hood is the same write byte function I have, and it's also including which register we're talking to, because when we want to send a command, we have to send that to the instruction register, but when we want to write data to the screen, like print a stick figure or print the flag, that's the data register. So I just have some wrappers around that to say whether we're writing a command or a data. And then these down here, this is the heart of the whole driver. These are the lowest level functions that interact directly with the LCD. This is how we're literally sending ones and zeros, and I think this is really cool. Starting with the write byte, that's actually the highest level function here. And because we're operating this in 4-bit mode, we actually need to split that whole byte into 2 nibbles, as they're called. A nibble is 4 bits. So we have 2 groupings of 4 bits. So imagine we wanted to send 10101111. We would be splitting that into sending 1010 first and then sending 111111. And how we're doing that here is we're calling this other function called write nibble, starting first with bit shifting that original number. This is being the original number we're trying to send. We're starting by shifting that to the right by 4. And what that's going to do is basically chop off these 4 ones and zeros right here, and that leaves us just with this 1010. And inside of write nibble, we start out by selecting the register pin, whether that's low or high, depending on whether we're trying to write a command or we're trying to write data to the screen. We set that first, and then we take that binary number, in our case 1010, like this, 1010, and we are going to translate that to toggling on or off the 4 data pins. And so we do that by ANDing the value with 1. In the case of the data pin 4, so that would be this value right here. So we're looking at starting from the right and we're going left. And with this value, we would be 0 and 1, and that's going to be a 0, in which case we're going to turn that pin to low. Followed by pin 5, we're going to do another bit shift, and we're shifting that over to the right by 1, which is like doing this. And now we're comparing 1 and 1, in which case it's going to be 1, and that's going to turn it on, and so on. And what we'll end up with is 1010, which is our binary data. And lastly, we call this pulse function. And pulse is going to temporarily turn on the enable pin, hold it for a little bit, and then turn it off. And what that does is it signals to the LCD module, hey, you should read whether or not these data pins are high or low and consider that part of our message. And then coming back full circle to the write byte, so we just did that for the upper foremost bits, and remember our original number was hypothetically this. So now we call write nibble again. This time it's only going to be looking at the 4 rightmost bytes that are here, which is the lower 4 bits, and it repeats. And so that's how we actually operate. We send a full byte of data over only just 4 pins. I think that's really cool. With both of the hardware drivers written, I was ready to tie everything together with the application code. Now, I already realized the video is getting a little bit long here, so I won't be able to cover everything, but I will sort of trace through the parts relevant to the map and rendering, because I think that's the most interesting part out of all of this. So I would encourage you, if you want more details, to please check out the link in the description below to the full repo, and you can read through the code there. But here I am in the main.cpp file for the whole code base here, and in the loop of everything, like once we get things up and running, we're basically doing this continual 3 steps where we first pull the game input. So we're using the joystick here, and we're determining where are we trying to move on the x-axis, as well as what the state of the button is, and then we pass that information to this function called game state update, where we passing in a pointer to a game state and the pointer to the inputs that we just pulled, and then it's going to change something about the game state based on that information. Lastly, now that the game state has been updated with the latest information, we can then render that game state. As far as the rendering goes, we'll take a look first at the game state, and I'll trace through some of the stuff related to that. So in the game state, we have a status. So we need to know, like, are we currently playing the game, won, lost, reset? And then we have this tile map, and a tile map is a grid of tiles, and the tiles I've defined are, it's either an empty space, a block, a spike, or the flag. And in this game, since it's kind of simple, the only thing that's moving around is the player. Therefore, everything else, it can be cleanly represented as being one of these tile types. How the actual map gets in there, so back in the main function, we have we have this load world, and we're passing in the game state, a pointer to the game state. So in load world, this is in its separate lib I have here. It's called world, and that keeps a clean separation of concern. So all the code related to how do we translate a map definition into something that's in the game state, that's what this library is taking care of here. And so you'll notice that I have this sort of ASCII map, which is defining what the world is. And so I'm using some symbols to represent different tile types. So if I have a hashtag, that's supposed to be a block. P, capital P, that's the starting position of the player. Capital F is the flag, and then the asterisks are the spikes. And what I'm doing then when I'm loading the world into the game state right here is I'm taking a pointer to that game state, and then I'm looping through this world definition. And for each of these characters that's printed there, I have a switch statement where I'm saying if it's a dot, that's just an empty space. So therefore, save in the map X and Y coordinate, say that this is an empty tile. And if it's a capital P in the game state, then I'm saying this is where the player X and player Y are going to start. And importantly, I'm also saying that that is also supposed to be empty space behind the player where he's standing. And so yeah, that's how I translate all of these into these tile enum values when the world is loaded into the game state. And then talking about rendering. So once we update the game state, we have things moving around. The player's at a certain position, the camera's at a certain position. We're ready to actually render something onto the screen using our game state, passing that in. So here, taking a look at this is where it ties back to what we were talking about earlier with bitmaps and custom characters. So I'm defining here my bitmaps. This is what the player looks like when he's standing still. I've got 2 frames of him moving left, 2 frames moving right, the block, and the flag. And I said 2 frames of left and right because I created something that is akin to a sprite. And all a sprite is a couple frames here and a frame index to know which one we're currently supposed to render. And as the player is running left, it's going to switch back and forth between which frame to paint, and that's what gives that illusion that there's an animation going. You can see his legs moving and he's going somewhere. So in the main loop of render, whenever we call render after we've updated the game state, we're first checking the status to see, are we still playing, in which case we're going to render the next game tick. If not, well, we lost or we won, and we need to say that text of saying you died or you won. When we render the game tick, what we're doing here is doing some math. The whole point of the game, and with the changing of the cameras, is giving the illusion that this 16:2 display is just a small slice, it's a small window into a world that is larger than 16:2. And so what we're doing here is based on the camera position, which during the game update function, we're calculating based on the player position. Based on wherever the camera is, we're going to do some math and look into that map that we had loaded and see which tiles exist that would be in view of this camera. And if so, wherever those are, then we're going to call this get tile bitmap code to figure out which bitmap code we want to call our LCD driver and say, hey, print this particular character. So in the get tile bitmap code, we're just doing another switch statement, and we're saying, okay, what type of tile is this? If it's empty, we're just going to render an empty space. If it's a block, then we're going to render our block bitmap, etc. And then for the player, we have up here, based on the player X and Y position, also relative on the screen, we then have some logic here that determines which bitmap code we're going to do there. And the most interesting case of that is whether the player is moving left or right. So if they're moving left, we call this get sprite frame at player left, the pointer to the player left, or player right sprite. And then inside of here, which is just defined just above, what we're doing is with that frame index, we're going to be taking either one of those frames, and then we're doing this OR operation here where we're going to toggle. If it's a 1, it becomes a 0. If it's a 0, it becomes a 1. And now we're ready the next time we call get sprite frame, it's going to be the other frame. So that's it for this video. Thanks for watching. I appreciate it. And again, if you'd like to take a look at the code, it's linked in the description below.